Well, I suppose we should start. I think it's about that time. So last time we were talking about computing the characteristic polynomial for a graph, and we're talking about the adjacency matrix. We'll move to Laplacian matrix in the next lecture, or maybe if you run out of material this lecture, maybe we'll mention it today. And so the characteristic polynomial is the determinant of x times the identity matrix minus the adjacency matrix for our graph. Now, of course, some people don't really care if it's xi minus a or a minus ix, but there are people in the math department who will fight you if you don't have the xi first. And so we'll not to avoid, I should say to avoid any conflict, we will follow that convention. And we saw that we can sort of think of this combinatorially. And so our combinatorial interpretation says, well, when you're computing a determinant, you're looking at all these transversals and you're saying, well, which transversals are non-zero? And then you say, well, how can we interpret that in terms of the graph? And what we have is, well, we have isolated vertices, we have edges, and then we have cycles of length 3 or more. And what it turns out is we say, well, for each cycle we get a contribution of -1. This comes from the sign portion of the determinant. When the cycles are at least length 3, I should say it comes from two places, the sign portion of the determinant and the fact that there's a minus there. Then you just have to keep track. When the cycle is length 3 or greater, then there's two possible orientations, which is why we have this 2 to a power. And isolated vertices are corresponding to when we take the diagonal term, and that's why we get x. And if we think about our cycle decompositions, let's just call them D, we say, well, let's have the size of D be the number of vertices which are in some cycle. And then what we have is, well, there's n minus I vertices not in some cycle, so those are our isolated vertices, so that's x to the n minus I. And then our weight of D, which we're doing in this manner. And I will say for other matrices that are associated with the with different graph matrices, you can do something very similar. Now, one special case, which we mentioned, and we did paths, but more generally we can talk about trees. And here, well, there's no long cycles in a tree. And we can do trees. We can also actually do more generally a forest. What's a forest? Yeah, it's a bunch of trees. So it's a graph whose connected components are trees. Isn't terminology fun in graph theory? It's like, what do you think a forest should be? Well, it should be a bunch of trees. Exactly. You know, they came up with some good ideas. So if we're a tree or a forest, in other words, there's no long cycle, well, then the only thing that can happen is we can have these matchings. And so what we'll get is that our characteristic polynomial looks like the following. And this is always dangerous for me to write this down, but okay, we'll try this. Sum over all k, we'll have x to the n minus 2i and negative 1, n minus 2k, negative 1 to the k, and then we'll have the number of matchings with k edges. So that's what we get. And this is not so hard to see because what's happens, well, our cycle decompositions are just edges. Edges and isolated vertices. And so if we think of k as our number of edges, n minus 2k, that's how many vertices we have. We have k edges, so k cycles, so that's negative 1 to the k. And then we say, all right, well, how many times does this happen? Well, one's for matching. So recall, matching is a collection of disjoint edges. We're not assuming anything about maximality here. These aren't maximal matchings, these are just all possible matchings. And let's do a quick example, which will come into play in a little bit. And so let's have one of our graphs will look something like the following. And I just want to make sure I get the right number of vertices here. And here we go. So here's the forest. One vertex is a tree. One tree is a vertex, the other one is a path. All right. So a couple of things we can observe. If I'm looking at the characteristic polynomial of two disjoint components, what can I do? I'm not saying that we will do it, but what can I do? What can you do? Or what can somebody do? So characteristic polynomial of disjoint components, what can you do?
Split it into the components?
Yeah, you just say, look, I have a cycle decomposition on one side, I have a cycle decomposition on the other side, there the twain shall meet. So in other words, what choice you make for one doesn't affect the other. And so the end result is it's the product. So you just multiply the characteristic polynomials together. Okay, we won't need to do that here, but that's one thing that could happen. All right, so let us find PA of X. All right, so there are 1, 2, 3, 4, 5, 6, 7, 8 vertices here. Well, how many matchings are there with no edges? Yeah, there's one matching with no edges. You might say that, wait, there's no matching with no edges. Oh, wait, you got to be careful here. Make sure, just because nothing happens doesn't mean it doesn't count. And so yeah, so there's one matching with no edges, which is to take nothing. All right, well, and I counted the vertices before, but now I've lost my track. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 vertices, great. All right, so here we have n equals 8. So that'll just help me remember. So we have x to the 8. All right, how many with one matching? Okay, so a matching is an edge. So it's the same as counting the number of edges. How many edges do we have? 6. So 6x to the 6. Okay, 2. Now we'll have a plus. And this might recall yesterday. You just sort of work your way through. It'll be 10. Yeah, say we fix this edge, 1, 2, 3, 4, and fix that one, 1, 2, 3, and this one, 1, 2, and then this one, 1. So sort of work your way through. 10. X to the 4th. Okay. How about 3 edges? This one might take a second. That's all right, we have time. So we can take 1, 2. So there's 1, 2.
Oh yeah, and you can move that one.
So I think there's 4.
Yeah, there should be.
So 4. All right. And are there any matchings which have which have 4 edges? Yeah. No. There's not. All right, good. All right, well, that's nice. And it will come into play in just a few minutes. I want to do another one, just to make sure we have this down. Well, the power of x is just, you think of, no edges, number of vertices. And one edge, subtract 2, because, 2 vertices and an edge. 2 edges, subtract 4, 2 times 2. Because each edge takes out two vertices.
Yeah.
All right. Well, I seem to have something amiss here. Oh, I know what I have amiss. I'm missing a vertex there. There we go. All right. So that's 1, 2, 3, 4, 5, 6, 7. Okay, good. N equals 8. All right. Now for this graph, let's do it again. Okay, no matching, still x to the 8th. Okay, 1 matching. 1 edge in our matching.
So it should be 7.
So it's number of edges.
6.
So there's 6 edges. Yep. No, we knew it too. All right. How about matchings with 2 edges? That'll be a plus, something x to the 4th.
10 as well.
Yeah, so certainly you can have 2 on the same side, and there's 1, 2 of those. Then you can have 1 on from each side. Well, here you have 2 choices, and here you have 4 choices, so that's 8. So 2 plus 8 makes 10. Cool. All right, now how about matchings with which involve 3 edges? How many are there? So there's 4. You have to take 1 from here. There's 2 choices. And there's 2 ways to take 2 from here. Is there anything which involves 4 edges? No. All right, cool. So what do you notice? Yeah, it's the same polynomial. So our great aha, these are cospectral. And do we have any idea what any of the eigenvectors are? No, we don't. Well, we kind of have an idea of what that eigenvector is, you know. And so, but no, I mean, I don't even know if it'd be easy to find the roots for this. It might be, but it wouldn't be trivial. So, all right, great. Now, this will make a comeback later on. Okay, probably should close my parentheses.
I'm glad, thank you. Yeah.
I know. Everyone's like, whoa, those parentheses, they're driving me crazy. All right, so I want to talk about something called coalescing. And you could also call it gluing. And I like to say gluing just because that's a word that I can spell correctly more frequently than coalescing is. But that is the correct spelling of coalescing. I don't want you to think like, oh, Steve just guessed on that. No, that is the right way to spell coalescing. And so the idea is what you do is you have your first graph, we'll call it G, and you have a vertex labeled V. And you have a second graph, we'll call it H. And it can be a different graph, it can be the same graph. It also has a vertex, and we'll give it the same label V temporarily. And the idea of coalescing is you say, these V's are actually not different V's, but they should be the same V. So we're attaching G and H at a single vertex. And so there's different ways to denote this. Oftentimes you might see a dot, and you can even put like the vertex underneath it to say, I'm taking G and H, and I'm identifying. That's oftentimes how it's phrased. I'm identifying this vertex as the same vertex. Okay. So let's take a minute and think about some various things. So the thing I want to focus on is what can we say about cycle decompositions in our G coalesced with H, or G glued onto H. And in particular, think about the gluing vertex. What can be true?
Well, if you have you can't have a long cycle that goes through, or it doesn't seem like you can have a cycle that goes through both of them. It has to stay in G or it has to stay in H. So then it would close off. It would be a close walk on it.
Right.
Like a finger.
Good. Okay, so you've hit the nail on the head when it comes to like what's there to understand here, which is to say, and this is our great aha insight, which is to say that cycles in the cycle decomposition, they pick a side, are completely in one of G or one of H. Now that's not to say that all the cycles are in G and all the cycles are in H. It could be that some cycles are in G, some cycles are in H, but as was pointed out, we don't have any cycle doing something where it spends some time in G, then comes back and spends some time in H, because that's not a cycle. You hit that vertex too much. And so that sort of says, okay, so what we can do is we can start thinking about sort of combining cycle decompositions. So we're going to look at a couple of things. So let's think about what happens, and okay, for notation's sake, I've been using P sub A. I'm going to replace this by P sub G, just so we understand. It's the graph G for the adjacency matrix. So let's think about the following. We can take P of G and multiply it by P of, all right, so this here, the way we're thinking about this, these are all the sums of cycle decompositions. Now, I'm going to look at multiplying by H minus V of X. Okay, so what you should think of is whenever you have a multiplication going on, and we know that the terms, individual terms, correspond to cycle decompositions, you should really think, okay, I'm combining a cycle decomposition in G with a cycle decomposition in H minus V. And I'm doing that in all possible ways. So that's what this product means. All right, does that capture everything?
You need to do P of G minus V times P of H.
Okay, so there's a suggestion we need to also include P of G minus V of X, P H of X. All right.
Subtract the H minus V and G minus V.
Okay, and now we're going to get more complicated. All right. So first off, let's make sure we understand what's going on with these terms. So here, what are the things that we include? Well, think about it from the perspective of V. So when we have our PG, PH minus V, well, we're definitely going to include anything where there's a cycle that includes V that goes into the G side. Now the cycle could just be a single edge, but anything that includes a cycle that comes in and involves G on the G side will be counted here. And in the same way, anything that includes V in the cycle and is on the H side will be counted here. But you said I should subtract something. What? And I think you were saying you should subtract P G minus V, P H minus V. Okay.
Possible V is neither then.
Correct. Well, if V is in neither, then what does that mean? Well, it's just by itself. It's an isolated vertex. All right. Now, is this correct? Well, it's an expression, so who's to say right or wrong? But is everything accounted for? And I guess the question is, does this equal just our coalesced graph? There's a suspicious amount of space there. If that helps, I'll point out that there's a suspicious amount of space there. So just think about it in terms of cycle decompositions. Every cycle decomposition should be accounted for.
Maybe like +1.
You need to account for V as its own cycle.
Right? So how do you account for it as its own cycle?
Just multiply x in there.
That is correct. That's the missing piece. And so really what this is, you can think of this as just the, in some way we can see there's three parts. There's the H and then, the G part, and then you have H minus V, you have your H part, then you have G minus V, and then you have it where you're missing both sides, and then there's an isolated vertex. And so then the characteristic polynomial of the isolated vertex is x. And so you're multiplying the three together. And if you just go through and say, okay, any cycle decomposition is counted collectively once. And then why do we include the minus? Well, if you have an isolated vertex, it could have been an isolated vertex on one side, or it could have been an isolated vertex on the other side. So it would have been counted twice, but now we subtract, and that gets rid of our overcounting. So if it feels like inclusion-exclusion, it's because it is inclusion-exclusion. So that's why it might feel that way. So, all right, good. Now, so this is just a general statement. So it helps us glue things. So here's a little fun fact which says, okay, just suppose for a second, so suppose I have two graphs, H1 and H2, so that I have that P of H1 of x is P of H2 of x. Okay, that just says they're co-spectral. They have the same characteristic polynomial. And I should have added a word here, rooted. So I'll add a word, rooted graphs. What does it mean to say a graph is rooted? Yeah, there's a vertex that says that vertex. That's like the starting vertex or something, the root. All right, so we'll call the root V, and we'll say P of H1 minus, well, okay, I'll just say root x equals P of H2 minus the root of x. All right, so suppose I have these two facts. Then the claim, so that's our arrow meaning then, if I look at P of G where I connect to H1 at the root, that's the same as P of G connect to H2 at the root. I should again think of G as there's a root, and I'm just joining at the roots. I'm being a little bit vague here, but not too bad. Why is this true?
Substitution.
Yeah, it's just saying these pieces here, it's just saying just compare what happens. You can swap out these pieces for H1 and H2. And then the G part doesn't matter because I'm keeping G the same. And so that I get these nice things. So in other words, it's a way to construct co-spectral graphs. Now, do we have an example of such a pair, H1 and H2? Well, I claim we do. And I'll draw a graph which will feel somewhat deja vu-y. And let's see if I can get the number right. Yep. So, take this graph, and this is H1 and H2. And at this point you're like, haha. It's easy. As long as H1 and H2 are the same, then you haven't done anything. Except, what haven't I said? What the roots are. So we'll put one root here. Call it H1 if you have that root there. And we'll put the other root here. Call that one H2. Now, is it true that these have the same characteristic polynomial, H1, H2? Yeah. Do we need to derive that, or is it just, or is there a simpler way to prove that? It's the same graph.
Yeah, it's literally the same graph.
Exactly.
All the same matching.
It's literally the same graph.
Yeah,
Okay.
same cycles.
Now, what if we delete H1 versus delete H2? Well, we should derive that. But we already did. And so,
In fact, yes.
yes, it came back. It's almost like we planned it that way. You know. Oh, it's the universe planned it for us. So,
What a coincidence.
and so, all right.
All right.
So, this turns out, this is a sort of a very nice result due to Schwenk. And what Schwenk showed is that almost all trees are cospectral. And I should explain what these things mean. First, okay, we know what trees mean. Cospectral means they have the same spectrum. Now, it doesn't mean that almost all trees have the same spectrum. But what it means, excuse me, what this means here is that almost all trees have another non-isomorphic tree. So there's a different tree out there which has the same set of eigenvalues. But you'll notice that there's this small caveat, the almost all. Okay, so does anybody know what that means?
Theoretically, it should mean there's a finite number.
Well, actually, no. That doesn't mean that there has to be a finite number.
Well, I was assuming that it's countably infinite.
The proportion of trees on vertices that don't have
Yeah, it's probability zero is the
advantage
actual.
is zero.
Right. The proportion of trees where this is not true tends to zero. But of course, so as the number of vertices increases, so this is a probability statement. It just says that the proportion, I like how you phrase it, so I'm repeating it. The proportion of trees where this property does not hold tends to zero. But of course, since the number of trees tends to a very large number, well, that just says that, relatively speaking, relatively few trees will have this property, but there can still be infinitely many trees which don't have a cospectral mate. So, nice thing about infinity, you can, almost everything could be true. So how did Schwenk prove this? And the answer is he found this pair of graphs, H1 and H2. And he said, well, what I can do is I could have a tree, and then I can glue H1 onto it. And if I glue H1 onto it, well, I shouldn't call this T1. Well, okay, all right. I already made my goof, but that's okay.
Are we considering infinite trees?
No.
So it's for sure a different definition than just the actual probabilistic over the whole set.
Well,
it wouldn't be considered almost none if you just take all finite trees and lump them together.
But there's infinitely many finite trees.
Yes, but countably infinitely many. So to have probability 0, it needs to be finite, which is not the case here.
That's not true.
How do you know?
Because if I say it's like the growth is n, and the number of trees is like on the order of 2 to the n.
No. I know what you're saying, but
Yeah.
it's not just a set. You're not saying almost all of the things in this set are blue.
If you try to find a probability distribution on the set of all finite trees, it's not 0. That is true. But if you look at the
Exactly,
probability
that's what I'm
distribution
saying,
on
is it's
trees
different.
and vertices, it is epsilon.
Exactly.
And the-
I agree.
Well, anyways, so the punchline here is that if you have a tree and you have this thing hanging off somewhere, which is H1, that's been glued onto a smaller tree, then what you can do is you can swap out. Because this is really the result of a coalescing. Say, okay, well, I uncoalesce with that, and then I recoalesce with H2. And then the result is something, and I feel like I've suspiciously have drawn too many vertices here, but, well, ignoring that I may have added an extra vertex, but the punchline is you can swap. So the swapping part is what we've shown. And so that's the part I like about the argument. But that's not the hard part of Schrenk's argument. Schrenk's argument, the hard part is to say, and the reason why there's a statement almost all, is to say, well, actually, if you fix a small tree, it doesn't matter which tree you fix, just fix a small tree, then with high probability, you pick a random tree on n vertices, n large, then somewhere that small tree is hanging off. It's been glued on. And so that's the part that's the most of the work. And but that's not a spectral graph theory result. That's just a graph theory result. So we're not going to go over that part. But it's a nice thing to remember. You know, if you take a large tree with high probability, any small trees in it. All right. And let's see, is there anything else I wanted to say? We should probably mention one other thing. This is not something which we may use, but it's true. And it's good to remember this. So if we're looking at our characteristic polynomial, I'll go back to PA of x, which is our again, it's our sum. And whoops, why did I start at 0? I should start at 1, I should start at 0, not 1. 0 to n, sum over all decompositions. Number of things in our decomposition is I. X to the n minus I, weight of d. All right, so that's one expression. What is another way to write PA of x? Well, okay. I don't want you to try to read my mind. I'll just tell you what I'm thinking. It's the product of x minus lambda I. Okay. So my lambda looks terrible. There we go. Now it looks more like a lambda. So what do we see here? Well, if you expand this out, what you get is that this becomes x to the n minus, and then you have your lambda 1 plus dot 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 plus lambda n, x to the n minus 1. So in other words, it's your sum of your eigenvalues, plus, okay, you have something, x to the n minus 2. What goes here? Sorry, what? Yeah, so it's always to pick two things, lambda 1, lambda squared, all the way up to lambda n minus 1, lambda n. And yeah, if I write things illegibly enough, then it must be true. Because I can just say, well, yeah, that's what I mean.
It's all combinations, or just the ones next to each other?
yeah, so essentially what you should think of it's, so you can write it in the following way. In fact, okay, plus, dot, 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 plus, okay, we'll have our sum, put a minus 1, okay, plus minus 1 to the k, sum, over all subsets of 1 through n. So this square bracket n square bracket means just the numbers 1 through n, where the size of S equals k of the product of everything in S, lambda I, okay, and then all that x to the n minus k. So yeah, it doesn't have to be pairwise. So it's lambda 1, lambda 2, lambda 1, lambda 3, lambda 1, lambda 4, da 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 da, and then lambda 2, lambda 3, lambda 2, lambda 4, you know. And so, of course, one of our nice things that we can get from this is that we can say, well, if I look at this product here, this corresponds, if you think about what's going on up here, because I have this x to the n minus I as well. And so this says, oh, this is the same as the sum over all cycle decompositions, which involve k vertices, the weight of that cycle decomposition. And so it's possible to connect certain types of cycle decompositions with the product of your eigenvalues. So, and there are cases where it's like, oh yeah, I see how the eigenvalues are entering in. Ah, that's useful. That's useful. Good. All right. And I think that's what I want to say about characteristic polynomials. So, should we start with Laplacians? Yes? It's a brave new world. Okay, so the Laplacian matrix. We've been waiting for this. And our day has come. So, we'll call it, well, I should introduce some things first. L is D minus A. Now, what is A? A is our classic adjacency matrix. What is D? This is the diagonal degree matrix. So, in particular, what we can say is Lij, or LUV, whatever you want to call it, it's the degree of I if I equals j, so the diagonal is the degree. It's minus 1 if I is adjacent to j, and it's 0 else. So this is what it looks like. So we can start with our PA graph. This is a classic example, not because it's that incredibly useful, but because it's super easy to draw. So label your vertices, 1, 2, 3, 4. And what do we have? Well, the Laplacian matrix, we have that the degree of vertex 1 is 3, minus 1, minus 1, minus 1. And it's symmetric, so that's nice. Degree of 2 is 2. Degree of 3 is similarly 2. And degree of 4 is 1. All right. Nice. Okay. Well, that's good. What can we do with it? Well, let's see if we can make any good conclusions. We don't have very much. We just barely defined it. But, all right. Anybody spot some convenient eigenvalues and or eigenvectors?
The all ones of eigenvector, or the all ones vectors.
Ah, okay, so we have a claim. The all ones vector what do we get when we multiply by the all ones vector? We get 0, right? Because it's the row sum. And we have the diagonal entry, which is the positive of the degree. And then the sum of the off-diagonal entries is, well, there's -1 for each edge, which is the number of edges is the degree. And so we get 0. So our first observation is, notice, this is for every graph. Whereas in the adjacency matrix, it was like, we wanted a regular graph. That's when we had the all ones. We were like, and that's when we were like, that's our favorite kind of graph because we have our favorite vector. Now it's like every graph is our favorite graph because every graph has the all ones. All right, good. Okay, so 0, always an eigenvector. Okay. Well, can we say more?
Valid, yeah.
Well, 0 arrow is an eigenvector. And 0 is always. 0 is never an eigenvector.
0 is always an eigenvalue. Yes. Can we go even further with that? Okay, so we can go further. So there's something called quadratic forms. Now, these used to be all the rage. Like everywhere was like, man, quadratic forms, they're so cool right now. And so people loved quadratic forms. But currently, quadratic forms are like, we don't really, they're fine, but they're not as cool as they used to be. And you might say, well, what happened to quadratic forms that made them so uncool? Well, it turned out it used to be hard to typeset matrices. They said, okay, well, how should we think of a matrix? They said, what we'll do is we really won't think of it as a matrix. We'll phrase things in terms of what's called the quadratic form. So it was this notion. Now, how does it work? Well, we'll come back to our polygraph. And what you would do is you would say, let's introduce some variables, and x1, x2, x3, x4, 1 for each vertex. And then we have our polygraph, Laplacian matrix. And we'd multiply x1, x2, x3, x4 on the right in this manner. Okay, now the first thing is you look at this and you're saying, this does not feel very quadratic. So we're going to try to convince you it is quadratic. And we'll go even a little bit further. All right, so how do you think about this? Well, one way to think about this is if you were to carry out this multiplication, what would you end up with? Like, what size matrix, I'll put that in quotes, would it be?
It's just a 1 by 1.
Yeah, it's a 1 by 1. Usually we just say, okay, we treat that like, an expression. Okay, so how do we figure out what the expression will be? Well, what you can do is you say, well, look, if I look at the ij entry here in the Laplacian matrix, I'm going to multiply it by xi and by xj. So what we have is this is really 3 x1 squared, then minus 3 x1 not minus 3, minus 1. Sorry about that. Minus x1 x2, minus x1 x3, minus x1 x4, and then minus x2 x1 plus 2 x2 squared minus x2 x3, then 0 x2 x4, minus x3 x1 minus x3 x2 plus 2 x3 squared, 0 x3 x4, minus x4 x1, 0 x4 x2, 0 x4 x3, and then a plus an x4 squared. So if you carry out that multiplication, that's what you'd end up with. All right. Now we can see why it's called the quadratic form. All these terms are squares. So quadratic. Can we make this look even prettier? answer is, well, yeah, certainly there's things you can do. You'll notice we have symmetry. The x1, x2, x2, x1, we can combine those together. And the x1, x3 combines with the x3, x1. So I run out of colors very quickly. The x1, x4 combines with the x4, x1. And the x3, x2 combines with the x2, x3. All right, well, that helps. But, okay, so if we do that, well, we'd have 3x1 squared plus 2x2 squared plus 2x3 squared plus x4 squared minus 2x1 x2 minus 2x1 x3 minus 2x1 x4 minus 2x2 x3. All right, that's one way. Can we get it even better? Well, if you saw something like a minus 2x1, x2, what would you like it to be part of? Where do you often see things like minus 2x1, x2?
x1 minus x2 squared.
Like an x1 minus x2 squared. What would you need to make an x1 minus x2 squared? What are we missing?
x1 squared minus 2 squared.
Hey, wouldn't you happen to know I have an x1 squared and an x2 squared? So let's go ahead, we'll say an x1 squared minus 2x1 x2, x2 squared. Yes? Okay, that's that one. Okay, x1, x3. Well, what would we like to make that? Yeah, okay, we'll put an x1 squared and an x3 squared. Cool, cool, cool. x1, x4. Okay, x1 squared, x4 squared, and x2, x3. X3 squared, x2 squared. We say, well, okay, hold on. What about the squares? We've used up 1, 2, 3 x1 squares. Oh, well, we had 1, 2, 3 of those. X2 squared, well, we had used up 2 of those. So that's x3 squared. We used up 2 of those. And x4 squared, well, we only needed 1 of those. So that's actually everything. So what do we have? Well, okay, as we go in our very roundabout way, we have x1 minus x2 squared plus x1 minus x3 squared plus x1 minus x4 squared plus x2 minus x3 squared. Interesting. Now let's see these pairs here. 1, 2, 1, 3, 1, 4, 2, 3. What are they? They're the edges. It turns out this is the sum I adjacent to j xi minus xj squared. And that's true for not just the paw graph, true for all the graphs for the Laplacian. So now, can we use this to say maybe one small thing? All right. We'll fit in one more small fact up here in the corner. Okay.
So this tells you that the Laplacian matrix is positive semi-definite, right?
Oh my gosh, you got my small fact. Okay. Yeah, so all the eigenvalues are greater than or equal to 0. Yeah. So this in particular, the Laplacian matrix is what you would call a positive semi-definite. It's positive kind of, right? That's the semi. Positive semi-definite. And that follows from the fact that if you look at the sum of squares, well, it's greater than or equal to 0. And okay. And well, we know 0 is an eigenvalue, so it's definitely semi-definite. It's not positive definite. Can't be, we have a guaranteed eigenvalue 0. Next time we will argue that if you know how many times 0 is an eigenvalue, you know how many components it has.